Hi everybody, Jonathan here. In this video, I'll be giving you my take on section 6.4, which is all about the physics concept of work. Now in physics, work is simply a way of measuring energy, specifically the energy of moving things. And when things are very simple, and you have something being moved along a straight line at a constant force, then the work is simply defined to be the force times the distance. However, when the force is changing, or when the object isn't something solid, then things get a little more complicated and we have to use calculus. Now you get a really nice formula in the situation where you have an object moving along a straight line and a force is being applied to that object, but the force applied depends on the position of the object. So if f of x gives the force applied to the object a position x, then this finding the total work done can be done in the classic calculus way of dividing the interval over which the object is traveling into subintervals. Over each subinterval, assume that the force is constant equal to f of xi star, and then the work done over that subinterval will be that force times the length of the subinterval, which is delta x. So we get that the Wi, the work over that subinterval, is f of xi star times delta x, and you get a lovely approximation. When you add all those up, it's going to be the sum from I equals 1 to n of f of xi star times delta x. And in yet another beautiful application of the fundamental theorem of calculus, we get that the work is the limit as n, the work will exactly be the limit as n goes to infinity of the sum from I equals 1 to n of f of xi star delta x, which is equal to the definite integral from a to b of f of x dx, which we can find with antiderivatives. So solving this first type of problem tends to be fairly simple. All you have to do is figure out what a and b are and what the force function is, and you go ahead and integrate. However, there is another type of work problem in this section, and it's a problem that's much more complicated. In this type of problem, you've got some kind of malleable substance, for example, maybe like rope, water, sand, oil, and usually it has to be raised up. In general, it just has to be moved somewhere, but it has to be raised up. So the work required to raise the particle of the substance, which is lower than another particle, is going to be greater than the work required to raise the higher particle, because lower particles have to be raised up further, so their distance will be greater, so the work will be greater. And there is no set formula for solving this type of problem. Instead, this type of problem is going to have to be solved by setting up a Riemann sum and then converting it into an integral. Now, I made this simple little GeoGebra activity to illustrate the principle of how this is done. So suppose we've got a cone of water. So basically, we've got some conic-shaped water tank, and we want to pump all the water out of that tank. How are we going to do that? Well, imagine that we slice the water into slabs. So here it's the same cone, but now it's all divided into various slabs. And then each of those slabs is technically something we call a frustum, which is a slice of a cone. But in order to make the volume calculation more simple, we can assume each slab is a cylinder. And then we can calculate the total volume of each cylinder. And then if we know the density of water, we can calculate the mass of each cylinder. And then we can calculate the work required to pump each cylinder up to the surface. And now, by taking the amount of cylinders, so kind of splitting up the interval over which you're raising things, to be larger and larger, you will always get a Riemann sum, and when you take the limit of that Riemann sum, you can convert it into a definite integral. And usually it's not that hard of a definite integral to solve, and you go ahead and get your answer. So let us try to apply these ideas to the following example. Suppose we have a water-filled basin, and it's the shape of a hemisphere, so the bottom half of a sphere, which has radius 5 meters. Now suppose the basin needs to be cleaned, so all the water needs to be pumped out. How much work will it take to pump out the basin? And for this, we're going to use that the density of water is 1,000 kilograms per meter cubed. And also, the formula for a hemisphere of radius 5 is, at least for the bottom half of the hemisphere of radius 5, is given by z equals minus the square root of 25 minus x squared minus y squared.